Hello everyone, I'm Mr. Rast, and we're going to start our lesson on 5.3 periodic trends. And the trends that we're going to talk about are atomic radius, ionization energy, electron affinity, and electronegativity. Before I get started though, I thought I'd share a story that a student just recently told to me. He transferred here from England, and he was giving me a little bit of, I guess, English culture or whatnot. He says, Mr. S, do you know what it's called when the Queen of England farts? And I'm like, I've got no idea. He says, it's a noble gas. Oh, goodness gracious. Okay, let's get going. So the first trend we're going to talk about on the periodic table is that of the atomic radius. As we move down the periodic table, the atomic radius gets larger. Moving down, so as you can see here, as we move down the periodic table, you can take any one of these columns, and as you move down, you see that the periodic table gets larger. So moving down in a group, groups are the vertical columns, shells of electrons are added to the nucleus. Each shell shields the more distant shells from the nucleus, and the valence electrons get further away from the nucleus. Protons are also added, but the shielding effect is of the negatively charged electron shields cancels out the positive charge. Let me explain. This is kind of a textbook definition. Let me kind of explain what's going on here. So we know that the first row is the first shell. So we've got this first shell, which just has got 2 electrons in it. We know that the second shell has the S block and the P block, and it has 8 electrons in it. So what's happening is every time you move down, whatever row you're in, you're moving from one shell to another. So this is the first shell, the second shell, the third, the fourth, and we're just adding more electrons to those shells. Now, you might think, why, that makes a lot of sense that the radius is getting larger and larger and larger because we're adding more and more shells. Definitely. However, something to think about that's mentioned in here is if we're adding more electrons, we're also adding more protons. Remember, all elements have the same amount of protons and electrons. So if you're adding more protons, they're going to be pulling on those negatively charged electrons more and more. But what's happening is as you add a shell, you're adding to the valence. So out here, this is the second, these electrons added to the second shell is the second valence, the third valence electrons, the fourth. And so let's take a look at the fourth. The fourth valence electrons are shielded from the nucleus by the first shell, the second shell, and the third shell. They're interfering. So if you think that you've got this positive nucleus, and then you've got this first shell, and then a second shell and a third shell of electrons interfering with that fourth. So these electrons out here are shielded. There's electrons don't want to be near each other. They're being repelled by that inner shell, but they're also being pulled in by the nucleus. So what happens is it gets further and further and further away, and you get a larger and larger radius. So in essence, what I'm trying to explain is that the protons kind of get negated even though there's more protons because you have more electrons shielding those protons from the outer shell. Now, strange thing happens here that as we move left to right, the atomic radius decreases. So moving from the left to the right across the periodic table, protons are added to the nucleus. So as we move left to right, protons are added to the nucleus, so valence electrons are more strongly attracted to the nucleus. So as we move left to right, because we're getting, so here lithium has 3 protons, but neon has 10. So as we're moving here, the protons, adding more protons, pulls those electrons together. So lithium has 3 protons and 3 electrons. So let's take a look at this here. So I'm talking about lithium, and on your periodic table you should note that lithium's got 3 protons and 3 electrons. The electron configuration is written right here, that it's got 2 in the core and 1 valence electron for lithium. Look at your periodic table and verify this. If you're not sure about what I'm doing here, please go back to the topic 4 on about electron configurations. So anyways, we've got 3 protons, and it's got 3 electrons, but 2 of them are in the first shell and 1 of them is on the second shell. So if you take a look at lithium, you have 2 electrons in the first shell. We'll say that's the first shell. And we've got 1 electron way out here in the second shell. Okay, now what's happening here is these protons are pulling on all these electrons. They want to be near each other, but the electrons don't want to be near each other, near themselves. So these 3 protons are pulling on these 3 electrons. This outermost electron, though, is not very affected by the nucleus, because the nucleus has a charge of +3, is pulling. So the nucleus is got the protons. It's got 3 protons in the nucleus, and it's being shielded. There's a shield here of 2 electrons in the core, which is making this 3rd electron out here not have a lot of attraction to it. So these guys are in essence blocking these 3 protons from this 3rd electron, and so it's got this large radius. Let's look at neon. Neon is also in group 2. Neon's got 10 protons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And its electron configuration is as follows: 1s2, 2s2, 2p6. So we've got 2 electrons in the core, and I've got 6 electrons that are out in the valence from this second shell here. So again, just like what I did with lithium, I've got 2 electrons in the shell. So remember, right here I've got 10 protons. I've got 10 protons here, and I've got now 2 electrons in the core. These 2 electrons are shielding the other electrons, but these other electrons here, they're not shielded very well. So these electrons here, we've got 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. These 8 electrons, that's from here, that's the 2 block. So this is our first shell, this is our second shell. These 8 electrons are not repelled much by this shell, and they're not blocked much. So these 10 protons are seeping their attraction right through this shell and pulling these valence electrons closer to the nucleus. Where in this situation here, these protons are being shielded quite well, so they're being blocked a lot and having a little bit of attraction towards this, but in the meantime this electron has also a lot of attraction from the shell itself. So in lithium it gets much larger radius than in neon. So neon and lithium, neon's radius is much smaller because of that, because the shell isn't very attractive. So as we move from the left to the right on the periodic table, as we move from the left to the right of the periodic table, the shell in this situation is still 2 electrons. There's 2 core electrons here, and these 2 electrons are shielding 3 electrons here, so they shield it quite well. But as we move to the right, there's 4 protons being shielded by only 2. And as we get way over here, we have now 2 electrons shielding 10. So 2 shielding 10 is not very good. It's not a very effective shell. So let's go to the next situation on here from neon. Let's take a look at what's going on with sodium. Okay, so we just finished off talking about neon, and neon would have 10 electrons and only 2 of them in the core. So we've got this again, we've got 2 of them in the core, and then we've got in the second shell here, I've got 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So these protons are not being shielded very much. 10 protons are not being shielded by 2 very effectively. In sodium, we have just one more proton, one more electron, but a whole big thing happens, a big change. So in sodium, the electron configuration is 1s2, 2s2, 2p6, 3s2. So what's happening with sodium is the first shell has, I'm going to put them over here, 2 electrons. Let's get rid of this guy over here. We have 2 electrons in the first shell, so that's our first shell. That's our first shell. And then we still have the same thing that's happening with neon. We have the second shell. So our second shell is still present. Oh my goodness. Just write for me. That's our second shell here. Has, again, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So I didn't draw it very well, but these should be about the same size. But this third electron gets way out here, because this third electron in the third shell, this one electron here, this electron, these 10 protons are being blocked by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 11 protons are being blocked by 10 electrons. This is a very, very effective shield from this one electron out here. So what happens is when sodium comes, this one valence electron gets very far away. There's a lot of repulsion. Repelling means getting away from each other. Man, this marker is horrible. I just don't know why. All right. Where are you? Oh my goodness. Okay. There's a lot of repulsion from this one electron to these core electrons. They're repelling each other, and because of that, they're getting further out, and this nucleus can't compensate very well. And so if we look back over at our situation here, so that's why neon was really small, but sodium got real big, because now everything that neon was is shielding the one electron, and we've got 10 electrons shielding 11 protons, so it's very effective. But again, as we move to the right, it gets smaller because now we still have 10 shielding, but argon has 18 electrons, so 10 shielding 18, it's not as effective. So we see that the atomic radius gets smaller as we move left to the right, because, main thing I want you to take away from this, because we're adding more protons. As we add more protons, the shield isn't changing as we move left to the right. The shell isn't changing, the core electrons isn't changing, but as we add more protons, the shell becomes less and less effective. So key thing here is as we move left to right across periodic table, protons are added. And as protons are added, the shell doesn't, the shielding becomes not as effective. So there's not much of a shielding effect as you move from left to right. All right. If you can understand those last concepts, it's extremely important to understand what's going to be building on with this. If you can understand the shielding that we talked about with atomic radius, if you didn't get that, please rewatch that and ask me some questions if you have any, because that's really kind of the launching point for everything else. So the next thing we're going to talk about is ionization energy. Ionization energy is the energy it takes to remove an electron. So these electrons are attracted to the nucleus. They don't just fall off easily. Even things that lose electrons relatively easy, it still takes some energy to remove it. It's like, I don't know, think of it like being stuck here like a magnet, and you actually have to physically remove it. That takes you some energy. So to remove one electron, or the first electron, is called the first ionization energy. This is the energy required to remove the first electron from an atom. So the energy to do what I'm illustrating right here, that is called the first ionization energy. When that happens, now the atom becomes positively charged. This is what makes a cation. So when you remove the first electron, that's the first ionization energy, and we can remove the second, third, and so forth. So energy required to remove the next electron from an ion is called the second ionization energy. If we remove 3, the energy required to remove the third one is the third. My point being, it takes a different amount of energy for each electron that you remove. As we move left to right across the periodic table, ionization energy increases. So as we move to the right, protons are added to the nucleus, increasing the positive charge. This strongly attracts the negative electrons to the nucleus. This directly relates to the radius. If you think about the radius of something, the closer it is to the nucleus, the harder it's going to be to remove it. The further it is from the nucleus, the easier it is to remove. An analogy that some of my students identified with was that if you're going to shoplift, I really don't know. I like if you're going to shoplift and there's a cash register, the cashier, the further you are from the cashier, the easier it is to remove the item from the store. The closer it is, the harder it is to remove the item from the store. I try to do a lot of analogies to click with the students, and this is the one that seemed to have clicked the best with this situation. Our society. So anyways, it's directly related to the radius. Now we're talking about ionization energy is removing things. So the closer it is to the nucleus, the harder it is, the more energy it's going to take to remove something from the nucleus. So as we move left to right, let's just rehash what we're talking about. The shells are the same. We have the same amount of core electrons. Like here, we have only two. On the second shell, we have 2 core electrons. And as we move here, we add more and more protons, pulling those electrons closer in because the shell is not being very effective because we're adding we're adding protons. And so as we move left to right, we find that it is more difficult to remove an electron, and ionization energy increases. As we move down, ionization energy decreases because, like we talked about before, as we move down, if we think about those Russian nesting dolls, as we move down, we're adding more and more shells. So this would be like the doll on the inside, and this would be more and more and more shells. And so as we move down, we find that it's easier to remove electrons because they're further away from the nucleus. We have more shells as we move down. So it's easier to remove them because they're further away. Now, the second ionization energy is the energy required to remove the second electron. So it's always more difficult to remove the second electron than the first electron. The second ionization energy will always be greater than the first ionization energy. Reason being, well, let's think about this. If there's 2 protons and there was 2 electrons, these electrons were repelling each other. They didn't want to be near each other, so they kind of spread out. If you remove one of them, it's going to be what's going to be left is going to have less repulsion. It's going to pull closer to the nucleus. And pulling the second one off will be more difficult because it's closer to the nucleus. This attraction is stronger. So second ionization energy is the energy required to do the second electron. As we remove more and more electrons, it becomes more and more difficult. So electrons are removed. As electrons are removed, ionization energy increases gradually until the shell is empty. Then it makes a huge jump. So if we take a look at the periodic table and take a look at sodium, the second ionization energy is much greater than the first. Well, let's see, why would that be so? Sodium is located right here. It's element 11. If we look right here, element 11. If I remove one, then I'm clearing out the whole third shell, and I'm over here. Now, all the electrons left over are in the second shell. So these electrons are much closer to the nucleus. So to remove 2 will make it much, much more difficult. So removing 1 electron is not so hard, but removing the second electron will be much greater. With magnesium, the first and second ionization energies are comparable, but the third is much larger than the second. So to remove the third electron from magnesium gets much more difficult. So magnesium can lose 1, and that's still in the third shell, and you can lose the second one. It's a little more energy to remove the second one, and then we get to now we're in the second shell, but to remove a third one, to remove from here would be extremely difficult. Well, not extreme, but it would be much, much higher energy than to lose the first 2. Aluminum, The first three ionization energies are comparable, but the fourth is much larger than the third. So in this situation here, if we look at aluminum, it's saying aluminum can lose 3 comparably easily. So aluminum loses 1, okay, then 2, because it's number 13, and 3, 13 to 10, it loses 3, and that's all comparable. Each one slightly more energy than the last, but to lose a fourth one to go to this situation here would take a lot of energy. So you'd see a huge spike in energy needed to go over here. And so what am I talking about? What do we, let's clear this. Let me illustrate this for you on like how I've seen chemistry questions worded with this idea. So you might say a question might look something like this. You might see the first ionization energy might be 15. The second ionization energy is 19. The third ionization energy happens to be 127, but the fourth, I'm not telling you units or anything because I'm just making this up. The fourth ionization energy is 139, let's just say. So on a test, you get this situation. You have these ionization energies, and I just made these up. You'd have real ones if you're getting tested on this, obviously. So you've got these ionization energies. It says it's an unknown element, and it says, okay, what element is it? Is it A, sodium? Is it B, calcium? Or is it C, aluminum? Okay, or is it, I don't know, D, is it carbon? Okay, so your choices. Here's the ionization energy for an unknown element, and which of these what could it possibly be? And then you might look at this like, I have no idea. We didn't even do any math on this topic. I have no idea what to do with these numbers. I don't understand what's going on here. Well, you do understand maybe a little bit more than you think you do if you reanalyze what we said here. As electrons are removed, ionization energy gradually increases until the shell is empty. Then it makes a big jump. Now let's look at that again. It's gradually increasing. 15 to 19 is a gradual increase, but then it made a huge jump at number 3, meaning it was able to remove 2 electrons relatively easily. So things that remove 2 electrons relatively easily are the alkaline earth metals, or group 2. Group 1 will remove 1 with relative ease compared to the second one. Then you'll see a huge jump in energy. Group 2 will can remove 2 of them, but then you'll see a big jump in energy. And group 13, or over here, can remove 1, 2, 3 to get to this situation. Then it takes a huge amount of energy. And over here, so forth, 1, 2, 3, 4, and then it will take a large group amount of energy. So if we look at our periodic table, how you solve this is we first realize that, this is probably going to be something that's comfortable having a charge of +2. Having a charge of +3 would be difficult for this. So let's look at sodium. Sodium has a charge of +1. Sodium wants to lose just 1, and then there's a big spike. So sodium would not be the ideal choice here. The next one is calcium. Calcium would lose 1 and then lose 2 relatively easy, but to go from 18 to 17 would take a lot of energy. So calcium is a good choice. Let's see aluminum. Aluminum would lose 1, 2, 3 with relative comparability, but the fourth one would be a huge jump because it would be very difficult to remove from this new shell. So aluminum would not be a good choice. And let's look at carbon. Carbon would lose 1, 2, 3, 4 of them comparably, but then the fifth one would be much more difficult. So carbon would not be a good choice either. So it looks like calcium would be the best choice here. Now, the trick is, or the key is, with questions like this, these choices will always be in different groups or different families. You'd have to know more and have to do some calculations if I was to actually give you multiple alkaline earth metals. From what I've told you so far, you wouldn't be able to differentiate difference in alkaline earth metals because they'd all have this big jump right here from this. The first two would be relatively easy. Why? Because calcium is like that. So that's relatively easy. To remove the third one would be the difficult charge, the difficult step. All right. So for each element, when the valence shell is empty, the next electron must come from a shell that is closer to the nucleus, which is much harder to remove. And this is the reason why what we were just talking about. The next concept is electron affinity. Remember, ionization energy is the energy needed to remove an electron, where electron affinity is the change in energy when you gain an electron. It's the opposite. Ionization energy is the energy needed to remove it, where affinity is talking about when you gain an electron. So when you remove something, you're becoming positive. So ionization energy is kind of forming of cations, and electron affinity, we're talking about those anions, the energy change when you gain an electron. So if you add an electron and it makes something more stable, then you give off energy. Things that become more stable are things that are anions, things that get a negative charge when they gain an electron. So things like the halogens, these guys get more stable when they gain an electron to get to that noble gas configuration. Oxygen, sulfur, they would gain electrons to become more stable. Nitrogen, phosphorus, they would want to gain. So as we gain electrons and you become more stable, you're willing to give off energy. If you give off enough energy, you might be able to, if the energy I give off by gaining an electron is strong enough to take it from something else, then the reaction will happen. So let's try to think about this. If the electron affinity, the energy I give off by getting an electron, is strong enough to match the ionization energy of something else, it's the same or greater than the ionization of something else, then it can actually take that electron from it. If the electron affinity is not strong enough to overcome the ionization energy of the other element, then no reaction occurs. And this is going to be have a lot to do with the lab we're going to be doing in topic 5. We're going to be talking about, we're going to be basically taking electrons from things and which things have a stronger affinity and ionization energy. This will all come into play in the next lab. But if gaining an electron affinity again is the energy that is changed when you gain an electron. If adding an electron makes it less stable, then energy must be put in. So let's look at some things where energy is less stable. So like the noble gases, it becomes less stable for a noble gas to gain an electron. They don't want to gain electrons, so you must add energy for them to gain it. They're not going to give off energy. The alkaline metals, they don't want to gain an electron. You have to add energy. The alkaline earth metals. So the cations and the noble gases would have a positive change. They'd have to gain energy to get an electron, where the halogens and group 17 and 16 and 15 would give off energy. So these guys here are the ones most likely to give off energy to gain an electron. So the overall trend is, when you move from the left to the right across the periodic table, the energy giving off when an electron is added increases. So as you move left to right, the energy given off increases. So let's think about that. So therefore, fluorine will give off more energy than oxygen. So as we move left to right, so nitrogen will give off some energy, oxygen would give off more, fluorine would give off the most. Remember, the noble gases do not want electrons. They're already in a stable configuration. So this trend stops at the halogens. So I'll try to write on this, my luck with this pen. So this trend stops with the halogens. Okay, this trend stops with the halogens. Noble gases are a no-go. This trend does not apply to the noble gases. It stops with the halogens. So it looks really bad, but oh, sorry. So electron affinities don't change very much as you move up and down. It's more of moving to the right because you're adding more protons. It pulls them in stronger, and you get and it gets stronger as you move to the right. So things to the right, the halogens, have the most electron affinity, not the noble gases. All right. So the last bit of vocabulary needed for these trends is electronegativity. Electronegativity is how strongly the nucleus of an atom can attract electrons from other atoms in a bond. It sounds a lot like electroaffinity. Well, because electron affinity, because it is. Electronegativities of elements are estimated based on the ionization energies and the electron affinities. So if you take these two concepts, put them together, you get electronegativity. And it follows the same trends. So the most electronegative element is fluorine. Remember, the noble gases do not want to gain. So electronegativity is how strongly a nucleus attracts electrons. So the one that's going to attract the electrons the most would be fluorine. Remember, noble gases don't. And the one that would attract electrons the least would be francium. Again, francium has a huge atomic radius, and it's got a positive charge, and things that are negative can be attracted because of that positive charge, but it's got a huge radius and a lot of electrons around it, so it's not very likely to pull more negative things towards it. Where fluorine or fluoride, when fluorine becomes fluoride, would be the most electronegative. It's got a small radius, and it's got a very, very ineffective shield at this point, and so it's going to pull electrons to it relatively easily. So that's the trend of electronegativity. Again, remember, electronegativity would be, would be over here. Francium would be, this would be the least electronegative, and over here fluorine, fluorine would have the most electronegativity. The halogens, the noble gases are not electronegative. They're as stable as you can be. So this trend goes up to here and it stops at the halogens, not the noble gases. Don't forget that. A trick question might be, what is more electronegative? Francium, fluorine, or helium? And if you remember the trend and you're thinking, oh, it gets more elective as we move up, you might think incorrectly that helium is the most electronegative, but it is not, because it's how strongly they attract electrons, and it's already got its configuration. So the most electronegative would be fluorine on the periodic table, least would be francium. So let's summarize the trends here. As the number of protons increases from left to right, as the protons increase, remember the shell stays the same. The atomic radius decreases. So as we add protons, it gets smaller. Ionization energy increases. So ionization energy increases, and electronegativity increases. So as it gets further to the right, it's harder to remove electrons from it, and it attracts electrons more. So basically, as you move left to right, I want you to remember the radius decreases, the ability to lose electrons increases. So taking something from over here is harder from taking something over here. Again, why? Because the radius is smaller. And electronegativity increases. So its ability, its attraction to get something, another electron, increases. Remember with this one here, though, the noble gases are not included. So we're not talking about the noble gases with the electronegativity. As we move down, we're adding more shells, like those Russian nesting dolls. We're adding more shells. And as you add more shells, the radius increases. And if it's a greater radius, then the ability to take an electron is easier. So ionization energy decreases. And finally, electronegativity decreases. The ability to pull an electron to it decreases. It's the bigger it is, the harder it is to attract another electron. This is the summary of the trends that we just talked about here. All right, your final workshop for lesson 5 The periodic table is here. And this just kind of sums up what we've been talking about here. So place the following elements in order from smallest to largest radius. So remember your trends that the radius decreases as you move to the right and as you move up. So the smallest radius would be the top right, the largest radius would be the bottom left. And so you look at these guys on the periodic table and figure out which ones would be the smallest and largest based on those trends. Go back in your notes if you need to refresh your memory on that. Which of the following has place these ones in order from weakest to greatest ionization energy? So which of these has the greatest ionization energy and which one has the least? Remember, greatest ionization energy would be the hardest to remove electrons from. So again, this would be the top right of the periodic table, and the bottom left would have the lowest ionization energy. And by the way, this is chlorine, Cl. The font doesn't show very well. It's not carbon iodine. Place the following elements in order from weakest to greatest electronegativity energy. So again, which ones of these would pull electrons to it the strongest and which would not? So put these guys in order. Again, look at your trends and look where they are on the periodic table. For the test and for this workshop, be able to explain what electron affinity is. So what is electron affinity? Be able to tell me why the second ionization energy is always greater than the first. Why does the radius of atoms increase as you move down a group? So here you need to not only know the trends here, but why. So why does the radius decrease or increase as you move down a group? Why does and also you should know for this workshop down, but you should also know from what's the trend from right to left and why. Why does electronegativity increase as you move across a period? So you need to be able to understand why with this too. So there's some trends and some understanding that you need to be accountable for this next test. I wish you well and good luck. And if you don't understand something, please come ask for help. That's what I'm here for. Thank you.